Very good morning, all. I'm sure now you have started working over graphs. I'm sure most of you are feeling much more comfortable with the adjacency list and adjacency matrix programming. I hope all of you have done some basic programming with the adjacency list at least. I hope many of you are clear about the DFS and you have done probably implemented also. But even if you have missed that, maybe try this. But I hope the previous lecture has helped with this to work, at least using global arrays of the corresponding which we discussed to have the visited and parent as array being taken. So visited and this array plus parent array you have taken. Why I am repeating all this is that today also we are going to use the similar, and today we are going to talk about the BFS. Not only the BFS, we are also going to talk of its design as well as its analysis. And analysis along with BFS, we are also going to talk of BFS analysis also. And not only that, there will be another significant learning which will happen today to know big O versus theta, where we can use big O, where we can use theta, and how to identify. And that all is going to be the talk of today. And along with that, we will also understand a concept related to aggregation-based analysis, which will be another new way of learning certain aspects. So today going to be very crucial discussions, although very easy and probably should not take more than 45 minutes, but very important. To start with, let's start with breadth first search. So as the word suggests, effectively this is going to be breadth based. Primarily, it means that for every uncovered vertex or any uncovered vertex which you have, say, unvisited or untraversed, once you start, earlier we said that we will go to first of its adjacent and then go in depth. Now we will say explore its all adjacents first. First, I will traverse or I will treat them all adjacents first. All is important. And then further explore its all, of course, unvisited adjacents. If they are already visited, not to be done. So it's unvisited. And then further explore each of them. So here, all adjacents will be initially explored before going to any of them further. That is the only difference. And more or less, this concept is very useful for even going for anywhere, which we call as a level order traversal. More or less, this also becomes a kind of a level order traversal, although we don't use the word for graphs, but level order traversal of trees, binary tree, BST, any tree, B tree, everywhere, if you talk of level order traversal, concept will be useful and very close to these. So these are effectively similar to BFS. Their level order traversal becomes nothing but programming will be similar to BFS program. So you will be using this in a lot of ways. Just let's have a graph so that we can discuss further. Let's have a one graph here. Say one has certain adjacents, let's say 5, say 3. Then I have 5 has adjacent 2, 4, let's say 3 also. And then 4 has 6. And maybe I have 7, I have 8, like this. Assume this also has this kind of a connection. This has this kind of a connection. So something like this, I assume. Now, so BFS says, effectively, first, let's say if I started from some vertex, say 1. Now, with 1, of course, I will say output will mean 1 displayed. And then after 1, adjacents of 1 to be traversed. Adjacent of 1, who are the adjacents? 5 is adjacent and 3 is adjacent. So the compared to DFS, the difference is, first I will say all these are treated as displayed and traversed. So one's adjacents to be traversed first, they come in the output. And in this order, they will be further processed again. So after initially one has been completed, then I will resume or to start with 5. 5's adjacents to be seen. Let's say now 5's adjacent are correspondingly available as 4 and 3 and 2. So from 5, I will go one by one. Let's say go to the 4. 4 is untraversed, so 4 will also get covered. 3 is already traversed. I'm not going to deep to any node first. First, this whole list will be covered. 3 is already covered. Then we come to 2. So this is already covered. Now 2 is to be covered. I will have 2. 5's adjacent over. So I will say now start with the next node. Next in the list is 3. So I will go and see on the 3. 3 is any outgoing, nothing available. So 3 is also covered. Then I will shift my concentration to the next traversed, which was a 4. From 4, its adjacents to be seen. From 4, 6 is also there. From 4, 1 is also there. So 4's adjacent are 6 and 1. And corresponding to 6 and 1, I can see 6 is uncovered. So 6 is unvisited, 6 covered. And after that, 1 is already traversed. Nothing to be done with 1. Now 4 is covered. Go to 2. 2 has no outgoing. So 2 is also over. Go to 6. 6 has outgoing towards the 2. Again, nothing to be done. And that's it. Of course, till 7 and 8 are not covered. So maybe as earlier we expected, we could have done something, but here there will be a change. So as on date, out of this 7 and 8 are not covered by this BFS. I'll say, to be precise, this is a kind of a BFS visit. Now, having said that, let's understand in DFS, what we implemented was, firstly, we had a DFS from where we called DFS visit. And DFS visit was a recursive and I was needed to be passed here. So this is a common practice. In BFS, normally only BFS visit function is used. Why? I'll just explain. But there is no hard and fast rule, but normally only BFS visit is used. And you have already seen BFS visit will effectively cover all vertices which are reachable through outgoing edges of this connection from the given source. From the given source. That means unconnected edges like or unconnected vertices or individually connected but not connected to this particular source. For example, 7 and 8 are not covered or are not traversed at all by BFS visit. Yes, perfectly fine. Similar was with the DFS also. In DFS visit also, if you remember, DFS visit will also cover only reached vertices or reachable from I itself. From I only. From I, whatever reachable, they got covered. They were covered or they were traversed, I'll say. But then in DFS, we also had one main function where we had a DFS with whatever parameters, void DFS. And then we had for I equal to 1 to n, if visited I is false, or if visited I equal to 0, Then I again called DFS visit with passing I also. So DFS visit called multiple times. Every time one set of reachable vertices were traversed. This was happening, and every time a different set can be covered. So I'll just resume. There was some click, and that's it. So one set of reachable vertices traversed, and every new call will have another set. So multiple calls were possible, and through multiple calls, different reachable sets could be covered. But with BFS, normally we do not have this facility. Although we can use, normally we don't use void BFS. Normally we don't write here for I equal to 1 to n and then calling BFS visit. Normally no. Normally this is not done, although can be done. Why we don't do? So the reason of that is use of a BFS in graph algos will be primarily through a source, will be mainly from a particular source, from one specific source. Hence, we are not interested to have the overall traversal through BFS, and most of the graph algos, you will use BFS for starting from a source. For example, a simple case could be that, like, I want to find out a route from Kurukshetra to, let's say, Bhiwani. Now, source is fixed, so I'm interested to have KKR or Kurukshetra to outgoing edges, all outgoing edges to be covered. Some of those edges could be going towards Bhiwani, some of those might not be, some of those could have a longer route, some of those could be useful, some of those could be ignored, but only outgoing edges from Kurukshetra are useful. Any other source vertex is not useful. If that vertex is connected via KKR, obviously from Kurukshetra, I will reach to that city, and then I will target to have towards Bhiwani, aim towards this. So aim is towards Bhiwani, and effectively source is desirable. Not that if I have a connection between Delhi and Agra, that has nothing to do with KKR to other routes. So I will not be bothered about other cities, other connections, other edges. On the other hand, DFS is used for all connected, all such components, all vertices and all unconnected components also, all disjoint sets or disjoint subsets of connected components. So this DFS will be used effectively for all consideration of disjoint subsets of connected or reachable vertices, connected or I'll say reachable set of vertices, which will get covered through single call, and hence DFS is primarily used in that way. So DFS along with the DFS visit used, and we say DFS plus a DFS visit are both used collectively in graph algos. On the other hand, BFS is primarily used as a BFS visit. And the difference being DFS visits are going to be with some I. DFS visit is also going to be with some I. I means the source vertex. And other calls to all unconnected ones will rarely be used in this case. So that is the difference. But when you study it in data structures, those who have probably studied in data structures, graph is also taught. So graph also taught there. In that case, you might have used DFS or BFS. Both should cover all vertices, maybe taught to cover all vertices. But from algorithmic point, may be taught to cover all vertices, even if they are unconnected. But from algo viewpoint, graph algorithm, because in this subject, our focus is algorithm. So Corman book also suggests that BFS, breadth first, is primarily needed from a source. Hence, we are studying that. Having said that, now I go for the coding aspect. We have already seen that in BFS, like I went in order of 1, 5, 3, 4 to 6. So I'll say what we covered for the previous graph was 1, 5, 3, 4 to 6. And effectively, you could see I started with 1. All of the ones adjacents were covered, but then later they were also needed to be covered or to be traversed for their adjacent one by one. Then 3's adjacent was covered, that also in that order. Maybe let's say 3 has all 3 adjacents, they could also be covered. So effectively, the order of printing also needed later all of them to be addressed or traversed again for their adjacents. So obviously, I can see no recursion needed. In this case, effectively, we don't have a backtracking, etc. needed, no resumption from the previous needed. And indirectly, I can see everything is in the order of traversal, order of initial printing. So the one which is initially printed, that is the same to be traversed again, effectively clearly indicating that a queue data structure will be used. So effectively, if you say in a DFS, you get depth first used and a stack gets used, but that is coming through recursion. We are not implementing stack explicitly. And in case of a BFS, effectively, my queue gets used, but obviously queue doesn't come anyway through automatic process. So we have to explicitly use it. We have to explicitly implement or code it, use or code it. So that is the difference. So effectively, I'll say I will maintain a queue, and in queue, I will keep on inserting the vertices to be considered for traversal, to be considered for adjacent traversal. And whenever one vertex is over, then I will be deleting from the queue and resume from the queue. Whenever over, whenever adjacency list over, adjacency traversal, I will say. Whenever this adjacent traversal over, take, or I'll say delete from queue next element, next vertex from the queue. This is what we have done effectively. So this is effectively the overall logic. Going towards the implementation, I can quickly write partial code again today, but later I expect you to do the coding mostly of your own. So of course, for this graph, you need whatever graph structure, whatever n, and you need your source vertex or I. So I'll just name them specifically for source vertex. Of course, this is an integer. The index number, vertex ID, it is the corresponding integer vertex number 1, 2, 3, say 1, 2, or anything. 1 to 6 or 8, anything could be the source vertex. All other data structures are known. I still use the same arrays, global arrays of corresponding picture of parent, visited, etc. So same concept I still continue. Of course, you can later change it to a common structure also used as used in Corban. Yeah, and I will say now I have to start with. So first thing is initialization what? I have to initialize because global array parent, etc., visited, etc., to be done. So my for loop of the I to be implemented, and I will say my parent I also to be initialized to be equal to 0. Similarly, my parent I to be -1, normally as we have taken last time. Parent we are going to use a sometimes later, and visited I to be made equal to 0. And maybe let's say this is what my initialization is. Then comes next part. So I say, now I start with the source vertex. So first thing will be, of course, I will say printf source. Source vertex is covered. That is the first point. As soon as it is covered, I can also say that the corresponding visited status to be changed so that in future this is not again visited. So I must say visited source v equal to 1. Now I have to traverse once adjacents. So I say traverse once adjacents and repeat the process for all adjacents first, and then repeat for all them also. So effectively, I need the same process to be multiple times repeated. Hence, I will prefer that everything let it be done in a common loop. So I will have somewhere loop downwards, and there I will keep on doing. So to start with, I insert this node itself into queue. For queue insertion, the common abbreviation used is NQ. So I say this is source vertex. For example, my source vertex was 1. So effectively, I insert into queue. This is what the coding NQ. So you have to implement insert queue, and this NQ you have to implement. Now for insert queue, use some array of integers because I can see integer being passed. So it is an array of integers, front and rear to be implemented. Take them global, take them anything, but this is what you have to implement. So you have to do the code also. Code this one also. So, but NQ, I know you know well, so I'm not going to bother. Then obviously I said till queue does not become empty, I will keep on improving. Also, I'll say I have to also implement some queue empty function. And if the queue is not empty, I have to do something. Now, what I have to do? Every time I have to start with the first available queue entry. Like initially I have pushed 1, and that 1 is to be used for its adjacent. So I will say I have to take out the first vertex. So I say u equal to dq. So dq means a delete from the queue, and I will say call this. So u why I am using? Normally the convention is to call uv to be an edge where I have from some vertex u going towards v, outgoing edge. So this is my starting vertex, or I'll say source vertex of this edge, and this is my destination vertex of this edge. So uv is a common edge used. Hence, anytime we use variable u, we are primarily showing that this is the source vertex of a directed edge, and then we will find out for that. So in first case, my source vertex was 1. From 1 onwards, all adjacents are to be used. So I say u will become as a nomenclature or a variable name for the corresponding one variable or vertex ID. So 1, which is a source vertex. Its all adjacents are to be traversed, meaning that effectively I have to write the code for its traversal, its adjacency list traversal. What I will do? So I will say I have to take a temp node. So it is a node data type, node star effectively. And I would like to traverse. What is this going to be? I have to give the adjacency list starting pointer to this corresponding to vertex u. U I have just found. Obviously, you are well aware what should be that code. It is going to be graph u. And obviously, now I have to traverse the whole list. So something like while temp not equal to null, etc., I have to traverse. What to do? Adjacency list to be traversed. So every time I will find out whether this corresponding adjacent node is there. If there, whether it is traversed or not already. If already visited, ignore. Otherwise, print all these and then proceed further. So first thing is I have to find out what is the vertex ID. That vertex I will name as V, and in this I should get the corresponding destination vertex starting from U. So U has adjacency list. For example, I said U is 1. 1 has adjacents as 5 and 3. So initially V gets 5 and later it will get 3 and so and so. So V I got as this. Now from this I will check. If V is already traversed, nothing to be done. So I'll check if visited V equal to 1 or visited V equal to 0, only then it is to be done something, otherwise not. So if it is untraversed, what I have to do? As I already said, first of all adjacents are to be traversed. Only then next step will come. So that straight away means, first of all, this printf of V. Second, treat it visited so that in future we don't again go into trap. Third, this V has got its a parent defined. So I should also initialize my parent for this V. V is the index number, for example, 5. So to node 5, I reached from U. So I will give this U. This is its a parent. What else? Now, this all is going to be further visited. So this node is traversed, but V's adjacents are again to be needed in future. So I have to NQ. NQ and V will be NQ'd because V was guaranteedly untraversed and later it has to be added into the queue and every time the queue will be used correspondingly. More or less coding done. I will see if something is left, I can cover. So if I try to see that, yes, I repeat, V is covered, 5 covered, 5 is not traversed, 5 is printed, 5 visited, 5 is parent done, 5 NQ. Next time, I again go back to the loop. This loop, temp is still on the same pointer, so temp needs to be shifted. Temp could be, I could shift here temp, but even if visited is a false, even if visit doesn't happen, temp must be shifted. So obviously, I can shift temp to next node in outside of this if and temp to be shifting to the next node. Of course, you know the syntax, but I'm not writing that anymore. And then you keep on repeating this process. Once adjacency list will be over, now what to do? Adjacency list over means from the queue, I have to take next element. That is already being done here. So I have this DQ. So effectively, this means then I can simply say, I can go back to the while loop of the queue itself. So while not queue empty, that function is being here, and that is that. So 90% of the coding then almost done. You have to verify if some step is written, if some step is missing. So correct that. If somewhere we have missed something or intentionally I have left, so you have to verify. But coding is almost done. And this process, you can easily see from here what will happen. Through this statement, 1 will be printed, done. Then in the queue, I have 1 inserted. At present, queue is this much. DQ happens. This becomes U and removed from the queue immediately. So U becomes 1 corresponding to U1. Now U's list will be traversed. This U is 1 corresponding to this one. The corresponding list will be traversed. You will get through this printing of 5 initially done. So here you will get 5 printed and 5 will go into the queue. So effectively, I'll say 5 goes into the queue. This is already removed. Then similarly, 3 will get covered. 3 will be inserted into the queue and nothing more to be done. After that list over, obviously, this DQ will mean now 5 to be taken out. So as in the previous graph, 1, 5, 3, 4, 2, 6, corresponding to 5, you can see from 5, I have got 4 being covered. So accordingly, 4, 3, 2 are the vertices of 5. So from 5, I will go, and now 5's adjacents are 4, 3, 2. So one by one, they will be traversed. 4 is not covered. So I will print 4. After that, 3 is already covered. So 4 traversed, 4 will be added to the list. 3 already covered, ignored. Then a 2 will be traversed. 2 will come to the queue. And then nothing else. 2 has, does 2 have any in next connection? No, 2 doesn't have. So corresponding to 2, again, 2 over. So now 5 was being considered. 5 has been already pushed, deleted from the queue. Then we will assume 3. 3 will be taken out. No outgoing edges. 3 will be taken out and removed. Go to 4. Take out 4. 4 will be taken out. 4's outgoing edges will be considered. Do we have somebody 4 from 4 outgoing? Yes, 6. So from source, now from 4, we will get a 6 displayed. And as soon as displayed, 6 also added. Later, 2 will be taken out. And correspondingly, I'll have 2 taken out. 2 traverse, no outgoing. 6 taken out, no outgoing, over. Receive 7, 8 are not traversed at all. And obviously, as I know. So this is the way it works. Let's do for the analysis part now. First, start with BFS analysis. So for analysis, input size is no more n. Input we will be considering as, because my graph is, so input sizes will be effectively cardinality of set E and cardinality of set V. Why? Mathematically, we say my graph is V and E. It is possible that number of vertices could be more than edges, or vice versa also, or number of edges, let's say number of vertices could be more than edges, or number of edges could be more than vertices. So anything is possible. Both sizes are going to decide. So both will be considered. See, in analysis, if I have one loop, for loop or any loop, I'll say if I have loop 1, which executes, let's say, m time, then there is another loop which executes n times. My complexity is said to be O of m plus n if both are independent variables. If both have no dependency on each other, I say loop 1 will execute m times plus loop 2 n times. M could be bigger, n could be bigger, so we don't make generalized. On the other hand, if I have loop 1 and within loop 1, I have loop 2, loop 1 executes, let's say, exactly m times, loop 2 executes exactly n times. So then I will say the complexity was order of m into n. But more than one variable can be as a part of complexity analysis. All input sizes are going to be all input variables or all sizes which are deciding the input size, they will be considered. All sizes of various inputs will decide the complexity. So in our case, the sizes are 2. V means the count of vertices, and E means count of edges. Cardinality of this is being considered. So both can be different. V set of count can be more of edges or vertices. So we will consider both. What is effectively V? For my discussions, N tells this. So N is directly telling what is V. So we can use V or N. What is going to be E? So E is count of edges. Effectively now, what I say, where is E countable? How do I find count of E? How can I mathematically tell what is E? Effectively, it is nothing but it is total count of all nodes in the adjacency lists, of all nodes or in adjacency lists. There are multiple adjacency lists. Effectively, it means if I have I equal to 1 to n, I will say length of adjacency list I, which is corresponding to vertex I, this is going to be equal to n, or this will be equivalent to total edge count. If it's a directed graph, so if there are, let's say, total 500 vertices and there are total 1,000 edges, so I'll say accordingly 1,000 edges will be somewhere in each of these adjacency lists, and this is, for example, if I say V equal to 1,000, E is 10,000. If I know this already mathematically, this 10,000 is distributed somewhere among the 1,000 lists, among 1,000 adjacency lists. Some list can have 5, some can have 0, some can have 10. So on average 10 each, but not necessary. So my analysis will be considering both aspects. Let's quickly do the analysis now. First of all, in BFS, what we did, initials, or I'll say BFS visit to be precise, this was my function. Step 1, I did initialization. How much time it will happen? I have already said n times, so I can easily claim this is said to be probably O of n, or indirectly I can say O of v. Later we will see whether O is okay or theta is okay, but for the time being, I can easily say O of n. Then step 2, primarily where I had Q while loop, and effectively in this I have NQ. Of course, accordingly, corresponding DQ will definitely happen. So corresponding DQ will also happen. Let's write in capital only so that you don't get confused. So you have to implement N and NQ and DQ also, but correspondingly both calls exist. This was second step. Within this, nested was a while temp loop. So this was going to execute. How many times this is going to execute? What is the maximum possibility? How many values can be pushed into the queue, or not pushed, I'll say inserted. Obviously, you know well, maximum number of each time a vertex is inserted, and traversed vertex is only inserted, traversed never again. So that means it is going to be n times, or I'll say precisely v times cardinality. Yes, this is guaranteed because in maximum case, it will be executed v times. As reachable vertices will be only inserted, so it could be less than v, but big O says, so I can easily say it is big O of v. Then within v, how many times this loop is going to cover? Well, you could easily guess. Yes, you could say maximum worst case or upper bound can be order of E, number of edges. So probably you will conclude by that my complexity or analysis is going to say V into E because this is nested one. Well, you are almost fine as per your current knowledge. You could guess it correctly, but now be careful. I say it is incorrect. It is incorrect, although you have done no mistake probably. But why I say incorrect? The question is, if I said V is 1,000, CE is, let's say, 10,000, what you said? That outer loop executes 1,000 times, and you said inner loop for each of them, for each of vertex you assumed, for each of vertex, you said this executes 10,000 times. Even if I assume all vertices are connected, reachable, perfect, so nothing left, but is it correct? No vertex has 10,000 edges. This is effectively never going to happen, or it is impossible. To be precise, on average, it will be executed, let's say 10 times. 10 edges only in each vertex, 10 edges in one list. So you have taken unnecessarily wrong. Summation of all adjacency list is 10,000. No list can have 10,000. And even if one, let's say, assume one vertex only has all 10,000 in worst case, then others will be empty. So why should I have for each vertex this count? This effectively becomes that you will traverse 1,000 into 10,000 times inner loop. But that is never going to happen. It is impossible. Inner loop will, now what we understand is, do the aggregation-based analysis. In such situations, this simple nesting-based logic doesn't work. You must analyze it using aggregation-based concept. I say, overall, how much time or how many time while temp loop will execute, while temp execution. Overall, combining all vertices. Can I tell aggregation? Yes, you can easily tell overall how many edges are there, and all of them are distributed among these adjacency lists. This is going to be exactly E times. For certain list, it could be, say, E1 times for some first adjacent list, E2 times for second adjacent, En times for the last one. Summation of this will be the maximum execution, and this summation is exactly equal to total number of vertices, edges in the E. So that is cardinality of E. So effectively, irrespective of outer loop time, irrespective of outer loop or Q, total execution is exactly known. Hence, I say that now that analysis will mean that my edge-related logic, this is going to execute exactly order of E times. So in my BFS visit, I will treat the things in a different manner now. Step 1, initialization. And I say this executes order of V times. Step 2 was related to Q operations. This I will have already seen that this executes again order of V times. And step 3, unnested in totality, without bothering of nesting, I treat at the same level in total, total of all nesting, total of all nesting calls will ultimately be order of E times. So I say all these three are independent. I will have a plus to all these analysis. So I say order of V. For simplicity, even if I forget the cardinality sign, I can easily write order of V plus order of V plus order of E. Of course, if you use the sign, good enough, but even if you forget, it is considered this. So I can say effectively, if I don't use the cardinality symbol, I can say order of V plus E, meaning order of a 2V plus E. 2 doesn't matter at all. Constants are not used, so I can say order of V plus. Then quickly going to the DFS analysis also. So DFS analysis, I have there two parts. One was a DFS function. There I had initialization, if you remember. Then I had for I equal to 1 to n, and I said if visited I equal to 0, then I had a call to DFS visit, and DFS visit with certain parameters. And then similarly, DFS visit, I had void DFS visit. And here I had certain execution recursively. So either you solve it as a using recurrence relation, find upper bound, etc., etc. But again, I say, let's go one by one. How much initialization will take? It was effectively n times. So I can say it is order of V. This step again being called order of V times. So I can easily see n times. This call will be generated order of V times. This call could be less than any time, less than order of V or anything. But how to solve this? This also is an aggregation analysis. Overall, how many calls? Overall guaranteed, again, as in BFS we said, this is going to be, total calls are going to be E times only. Exactly E times. Because all vertices, all edges will be guaranteedly covered. And once any edge is addressed or covered, that vertex will be treated as already visited. It will never be done. So for each adjacency vertex or for each vertex, its adjacency list will be once covered and exactly once covered. So irrespective of a nesting, although here also nesting happen, but nesting will not be used for analysis. So I will say this takes this much time, this takes this much time, and I will claim without nesting, total, or by all nesting, I'll not say without nesting, I'll say by all nestings, the total is going to be order of E. Summing all this, the same thing will come, order of V plus E, it becomes order of E, V plus E. So you can easily see both have almost similar complexity, but quickly coming to one discussion O versus theta. Now understand how these two are different. Let's start with BFS analysis. This step I wrote O. Yes, perfectly O is fine, but can I say this will be always V times? Because initialization means guaranteedly n times. Any kind of a graph happening. So I can easily say this initialization is actually theta of V, although I can write O also. Q operation. Is it O of V okay? Or theta of V can be used? Theta of V can be used if it is in all kind of graphs. It is possible guaranteedly that all vertices will get into the Q. All will get inserted and then deleted. It is not true because reachable vertices will only come into the Q. In DFS visit, some nodes like 7 and 8 were never into the Q at all. Hence, number of vertices could not be all covered in some situation. This will mean I can't claim this to be theta of V. No. Then step 3, order of E guaranteed. Can I claim this to be theta of E? Again, like edge 7, 8 will never get traversed. Many more like this will not get traversed if they were not reachable vertices and corresponding edges or corresponding all adjacency lists will never get traversed, will not get traversed or printed or displayed. Hence, some edges and some vertices might not get covered. So I can say I can't write it as theta of E. So this can be written as theta of V. This has to be V of E. This has to be O of E. So this is O of V, O of E. And because now I'm combining, this has to be written as O. This has to be written as O. This has to be written O of V plus T. On the other hand, look at the DFS. Here I wrote O in the first initialization step. Can I write this to be theta? Yes, exactly n times, irrespective of any graph, any less or more connections, it will be always a theta of V. This, visited I true or false, but it will be checked always n times. Because in DFS visit, lesser calls, but a DFS call, all vertices covered. In the BFS visit, we already said all are not targeted, only reachable targeted. But in case of DFS visit, or less covered, reachable, but through DFS, all covered. That will mean by this call also can be claimed to be theta of E, theta of V. So this O can be written as theta. Similarly, DFS visit will be called multiple times. And even if certain unreachable edges or vertices existed, which could not get covered in one recursive call, later a recursive call will come and that will cover. So edges like 7, 8 by another call will get covered. And if so, I can easily say that all edges will get guaranteedly covered. Hence, this also can be considered to be called as theta of E. So in case of my BFS, everything can also be said to be theta of V or theta of E also. Hence, to be precise, I can write here theta of V plus theta of V plus theta of E, and then I can finally conclude this. So in a BFS, my answer is a big O of V plus E. But in case, or because it was only BFS visit, I'll not say write BFS. So I say BFS visit, and I know that this is O of V plus E, and a BFS call is actually going to be theta of V plus E. To be precise, equivalently, if I consider the DFS visit call and its analysis only, so that will be obviously O of V plus E, because lesser calls could be possible. Similarly, if BFS function existed similar to DFS, that probably will also lead to overall complexity of that leading to theta of V plus. So you can now easily understand how O versus theta differ. So with this, I hope you are clear with this concept, and you must remember this whole time, and you get a better clarity when to use better now, or when to use better clarity of using theta versus O. So you should know where theta is usable, where theta is not. O can definitely be used anytime, but theta, you must know, is it possible or not. With this, I'll wind up and stop. Best of luck to all of you. But now we are going to start various graph algorithms within which DFS and BFS visits or DFS and BFS traversals will be used very frequently. We are not going to explain that again, and you must be clear before the next lecture about all this. Bye-bye. All the best to all of you. Have a good day. Enjoy. And let me just stop sharing and stop recording.